if you recall from the question that we were doing, example number 2, yeah, yes, can I have someone come over to the residence to make the grades on because the display is not coming up. The computer works fine, but it's not talking to the screen. Yeah, it's it. Yes. The remote, yes. I can switch the TV on and off, but it's not talking to the computer. You know what I mean? Right? Yes. Thanks. Thank you. This is Cole. Yes. Yes, yes. Thanks. Can you find the test? I kind of share this with the test was the one that we did, right? So it's reject the null. Yeah, so the wrong case. So the test is you reject the null that X or the observed value is more than this one. So you're checking also correct. Yeah, reject when it's more than. So you're trying to find type 2. No, type 2 error happens. Yeah, that's actually correct.
So I just use 1 to 1.
Power is always 1 minus 9. So do type 2 first. That's right. Right. So
wait, if it says the alternative is equals 15, it's a little bit less clear than when it's just like greater than, equal to, or not equal to the null.
no, the human tracer lemma which we covered on Thursday, it involves a simple versus simple hypothesis. So it's no longer like a loop. So you're looking at the now saying that it's 10 versus the alternative image. So that it's like in the whole universe, there's no other value of just these two.
Okay.
That's it.
Well, check it out.
Alright.
Or you are safe here for the.
No, hopefully. The computer is fine. It's just it's not sending a signal to.
Yeah.
Mhm. And I'd like to see what you do, so in case next time this happens.
I'd like to see what I do too. Sure what I'm gonna do. Yes.
So what was the matter?
This button just has PC on it. If you click the other one, then it doesn't register. So
So which one should it be?
it should be PC. So if you click PC, it will pop up.
Okay, that was the one that was lighted, so I don't know what.
It was this one that was,
Oh, really?
yeah. So this one was lit up, and so
Oh, okay,
that switches it.
Oh.
If you have a laptop plugged in, you can switch to laptop.
okay. Okay, thank you.
Yeah, of course.
Yeah, so the test that we derived the last time was actually to reject the ground when this happens, all right? And so you need to, of course, know what is the error history. Because when you compute a type 2 error probability, the type 2 error assumes that you did not reject the ground, but the alternative is true. So with that fact, you can compute this probability, which I think we're done with, right? All right. The reason why I'm asking you to compute this is I want us to compare next time when we do a better test, to see which one is better for. All right. So was it okay?
So is there anything this person interested in?
No, not necessarily, because here you're saying that you have chosen not to reject it, but the null is false,
Oh, no.
and actually the alternative is true. So the alternative.
Oh, it's true.
That's right.
Is there anything?
And so of course now we can use actual standardizing to get ones.
Oh,
Right?
no.
Okay.
And are we using a 68.58?
You have to, because the, I will go through again because the NP lemma was covered in the last class and it's a very, very important thing. So if you don't know what the lemma is, there's no way to actually solve this problem. So I'll go through it after we're done with this. So I'll very quickly review the NP lemma. The Neyman-Pearson lemma actually is a very, 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 very important thing. That's the basis of the theory of hypothesis testing. It basically says that if you want to test a simple versus simple hypothesis, so what do I mean by simple versus simple? A simple versus simple hypothesis just means that the null hypothesis only gives one value for the parameter. The alternative only gives one value. So it's not what you're used to in intro stat. In intro stat, it's things like mu is equal to 5 versus mu is greater than 5. That kind of hypothesis, mu is greater than 5, is called a composite hypothesis. The Neyman-Pearson lemma is not even interested in a composite hypothesis. It's just interested in a hypothesis that the null says the mu is something or just one singular value, and the alternative is a singular value. So what the lemma is a prescription for generating the most powerful test that you can possibly form, if that's your pair of hypotheses that you're testing. And the basis for that is you write down the likelihood function under the value prescribed by the alternative, and you divide by the likelihood of the function under the value of the parameter prescribed by the null. And if your test is of its form, reject the null if this ratio is more than k, you have actually generated the most powerful test you could possibly form. So you need to, of course, have a few disclaimers. You cannot compare tests with different significance levels. You need to be in the same ballpark. So you first have to find what k is so that the test has a certain prescribed type 1 error probability. And that's what we did the last time. So the example we're talking about right now is example 2. So in example 2, we have this scenario. We have a normal distribution with an unknown mean whose variance is 60. And this being a simple example, we start off with not even n points, data points, we start off with just one. We only have one observation that comes from the normal with an unknown mean but a known variance 60. We want to find the most powerful test to test this versus this. See, simple versus simple. This is the value of mu under the norm. This is the value of mu under the alternative. So what does the Neyman-Pearson lemma say? The most powerful test must have form reject the null if something is more than k. Now, what's that something? Anyone? According to the Neyman-Pearson lemma, what is this something that must be more than k? If this is too big, yes.
So what is the function of the
The likelihood function with the parameter value prescribed by the alternative divided by the one under the now. Correct. Good. So you need to have the likelihood when mu is 15 versus the likelihood when mu is 10. And so if you do this, and this was another group work that we did, you'll find that this, well, for a normal distribution, the likelihood is like this. This is just one observation. Why 15? Because under the alternative, the mean is 15. Under the null, the mean is 10. So form this ratio, and this is greater than k. So when you have this kind of thing, this was our group work the last time. This form is not very useful to people. It's hard because you can't find what k is in this form because you don't know what is the distribution of this. However, if you do a little bit of algebra, a lot of cancellation will show that eventually you can, and this is group work 27. You can show using a little bit of simple algebra that this is equivalent to saying this. Why do we like this? Because this just means the test is essentially saying reject the null when y is greater than some number. I think the biggest disconnect people have with Neyman-Pearson lemma is they know what this step looks like, but then they don't understand why they always need to convert it. You need to convert it to something that you can find the type 1 error probability. So this statement is equivalent numerically to saying, well, this statement can be reduced to saying that y is more than something like that. And so our next job is to find what K star is so that this test has size or has significance level alpha. And we are choosing our famous 5%. We want our type 1 error to be 5%. So you need to find y greater than K star when y is normal 10, 60. Can anyone tell me why 10 here? Why not 15?
Because we didn't reject the.
It's not an issue of whether we reject or not. Why is it when we want to find K star, we say find K star so that this probability is 0.05, and how do I know that U is 10? What am I doing? What is this step trying to do?
Oh, well, if the probability of y being greater than k star is greater is. Oh, wait, I think, oh, never mind, never mind.
So you see, the test under the Newman Pearson lemma is that it has to have this form. This reduces to this. So what is the purpose of this step? Why do I want to find K star so that this probability is 0.05? And how am I so confident that I put 10 here?
Not actually confident because the probability y is greater than K star at 0.05 is that right? So technically.
That's right. You want to set the type 1 error of the test to be 5%. So when is type 1 error evaluated? Type 1 error is evaluated. Type 1. When the null is true, and what does the null say anyways? Now, with this information, are you able to get K star? Of course, this is just simple standardization. You know the distribution. See, the whole point of the Newman Pearson lemma is it gives you a prescription, and then it goes to it. It's your job to set what this number should be to give people a rule. And you can only find this number if you are willing to set a certain significance level and just for simple purposes, you get 5%. So you do standardization. I believe the answer was it 16.58 or something like that. You should find what they start with 16.58 or something like that. Okay. Then what I asked you all to do now was to acknowledge that the most powerful test, according to the Newman Pearson lemma, is I want you to reject the null when y is more than 16.58. So what equals 28 was all about was now this test has a power. Now, does anyone remember the definition of power? Or maybe, okay, it's 1 minus probability of type 2 error. That's right. Now, what's the probability of type 2 error? See, I'm trying to break it down so that systematically, so that we understand what we're doing. So, the probability of type 2 error is when you. What is a type 2 error?
A type 2 error is the error that you want.
You make the type 2 error, then what happens? That's right. So, how do you translate that information to this rule? The rule says I will reject the null when this happens. So, which means if I decided not to reject the null, what kind of y would I see?
Something less.
That's right. So, in other words, what are you supposed to find? You need to find the probability that y is less than this, but what's the value of u?
Oh, well, then the value of u is going to be back to 10 because of the.
It's not 10, is it? Because if it's 10, what's true? The null.
Oh, so we're trying to find a less than while we're using the alternative method.
Yes. See, these ideas are not hard, but they can be very confusing. You have to think. That's why the definition of the error is very, very important. So that's what we're going to need for this test. And I believe the answer is the power is only about just about 35%, something like that. Not very good. Low, not very high power. Why is this test so bad? Because this test is just based on one observation. Now, one thing we talked about last week was, does this test even make sense? You are trying to test this versus this. So it just says, if my y is more than 16.58, I will reject the null. Which makes sense. Your y is quite big, it's quite far from 10, I should reject the null. So the test makes a lot of sense, right? The only thing that our trade class doesn't understand is what's the definition of type 2 error. Type 2 error is I decided not to reject the null. And that happens if the y I see is less than this, and the alternative is true. and then you standardize the answer. All right. Okay. So that I think catches us up. So now we will look at another example. Use the Neiman-Pearson lemma to derive the test for same null and alternative. See, the whole point is we are still interested in testing simple versus simple and versus 15. But now look at the twist. I now have n observations that are independent, all from the same distribution. See, the mean is still unknown. Variance is still 16, so I want to be able to compare this test is superior. This test should have superior power to the other test. Okay, I know example 2 is very synthetic. It's a toy example because we're just using one observation. Who tests things based on one observation? It's extremely foolish to do that. But the idea is important to get. So we want to compare. Now, we're testing the same scenario, 10 versus 15, and versus 15. But now I have n IID observations from the same normal distribution. Do you get it? Last time I only had one. Now I have more information. So let me ask you a question. When you have n things like that, what do you think the rule is going to look like in the end? Reject the null here. How is it going to incorporate information from all these? And what do you think? What's your most intuitive guess for the statistic that's going to appear in the rule? Reject the null when? How do you incorporate all this information? You have done so much statistics since you came to this school. What do you think is the statistic that's going to appear in the rule statement? Reject the null when? You can't reject the
Y bar.
Y bar. It's going to involve Y bar. Good. The statement for reject the null when Y bar. Yes, that's where we're going right now. So I want us to look at group work 20. Hold on.